In the previous videos, we mentioned about the analysis and design part of your assignment. You first need to know the project in terms of the design scope, as well as the conditions of the project in various aspects, such as the material use, the soil conditions, the exposure conditions, and others. You need to know how to use the code of practice for you to complete your design. As far as the design is concerned, you're going to refer to the Eurocode, EC1 and EC2. As for the analyzing the loads acting on the slab and beam, EC1 and EC2 do not provide any provisions. Under such circumstances, you can actually refer to the BS at 110 for the analysis part. The idea is this: whichever being stated in the Eurocode, that will be the ultimate reference. Whichever is not stated in the Eurocode, you may refer to the closest standard, which provide guidelines, such as the BS at 110. Whenever there are contradictions in terms of the information given in the BS and Eurocode, the Eurocode should be ultimate reference. Next, you need to consider for the local practices, which we have discussed in the previous videos. You need to aware of the work conditions and the challenges for the contractor to work on site. Your design cannot solely fulfill your technical aspects without considering the needs of the contractors. After all, every party is working under the same project. For the contractor to deliver the structures in the good conditions, it is also a part of your success. Therefore, you should make your design and analysis, as well as the output of your design, which is normally presented in the technical drawing, to be friendly and applicable for the contractors. Sometimes you cannot expect any ambiguity occurs in your technical drawing that the contractor will come back to you and seek further clarifications. They are also in the tight schedule, which they may not have the luxury of time seeking for your clarifications and waiting for your response. If your technical design is not friendly enough, or there are ambiguity in your technical drawing, there is a high chance that they will modify in accordance to their experience, or they make their own assumptions on basis of certain guessing or experience that they acquire from the other projects, which in case of anything happen with the structures, both sides will have to take the responsibility. Therefore, it is always a good practice of you to make it as friendly as possible, not to make the work in the site troublesome, and have close supervisions with the works carried out on site. Now we will proceed our discussions on the common materials that are available in the industry. Of course, there are more, but these are the common size that a typical project will use. First, let us look at the common bar size that are available in the construction site. There will be mild steel bar, which in terms of your design, the specified yield strength is 250 Newton per mm square, and it is normally given in the size of R6, R8, and R10. We mentioned that R10 is not really common in the construction site, although it is achievable, just that because of the size of the rebar, it will be more difficult to be bent manually. Therefore, the site worker will prefer to use R6 and R8 instead. These are the typical mild steel bars. The surface is smooth and the strength is slightly lower. It is easier to bend as compared to high-yield steel bar. The mild steel bar are normally used for the shear link. Next, it will be the high yield strength steel bar. The steel bar will look something like this. The color is more bright, which is in fact an alloy, a mixture of the ferrum and the carbon, in order to increase the tensile capacity of the material. There are three common grades of the high yield steel bar, which are 410, 460 and 500 Newton per mm square. It is now more commonly of 460 and 500 Newton per mm square. And this high yield steel bar have the ribs. What you see, there are some patterns on the surface of the bar. We call it as a ribs. This ribs is important for the interlocking with the concrete. That is the one that contributes to the bond strength of the steel bar. In order to ensure good bond between the steel bar and the concrete, the steel bar needs to be fully embedded within the concrete and in direct contact with the concrete. Then this rib will serve to interlock with the concretes. There are quite a number of patterns in terms of the ribs. Sometimes if you view from the side, it looks like a Y, or it looks like a T, or it looks like a H. That's why you see sometimes there are bars being termed as Y10, T10 or H10. Basically, they all refers to the high yield steel bar. The common size of the high yield steel bar, it will be 10 mm, 12 mm, 16 mm, 20 mm, 25 and 32 mm. You need to be careful. There are no size smaller than 10 mm. This is a common mistake by our students, not aware of the standard size that are available in the industry. The smaller size for the high yield steel bar, it will be 10 mm. In fact, you can have larger high yield steel bar greater than 32 mm. However, the problem it will be, it is heavy and difficult to work with. When the bar size is greater than 32 mm, first, it is difficult to bend. Although there are bar bending machines on site, but you know that the reinforcement bar come in a long piece, which is typically in 12 meters, which cannot be handled by one person due to its weight. Another reason for this, it will be you will have difficulty to be installed in the small beam sections, as you need to cater for the cover of the beam. On the both sides, there will be shear links, and if you use significant bar size in a thin beam, most likely you have difficulty with the minimum spacing between the reinforcement bar. As for the typical usage, Y10 steel bar are meant for the slabs. As for the steel bar for the typical beam, the smaller size that you can use, it will be 12. Normally we don't use the reinforcement bar smaller than 12 mm for a beam. That is the local practice. And the most common size that you're going to use in the typical structures of less than 3 stories for the residential, office and commercials, it will be 12, 16 and 20. Sometimes you go for 25. It will be quite rare of you going for 32. This comes to our next point, the common bar size used in the industry. For the slab, it is normally 10 mm. It will be quite sufficient. It is especially when the span of the slab is less than 8 meters. As for the beam, we will use the smaller size of 12 mm and more commonly 12, 16, 20 and 25. As for the shear links, it can be either mild steel bar, which is R6 and R8, or high yield steel bar, which is Y10. There is no size smaller than Y10. Although the design of the shear links in accordance to the Eurocode, it will be based on the high yield steel bar. The reason is due to the better bond quality. between the steel bar and the concrete. However, the local practice still prefers to use R6 and R8. Next, it will be the reinforcement steel mesh, which is typically used for the slabs. You know that the slab is a big piece of reinforced concrete member, which is in the plank shapes. You have relatively large cross sections of the concrete as compared to the amount of reinforcement bar. Therefore, the reinforcement bar are normally adequately spaced out, typically in the range of 200 mm, 250 or 300 mm. There are few ways for you to put the reinforcement bar for the slabs. One is laying the reinforcement bar one by one in accordance to the size and the spacing, which is also quite commonly done in the local industry. Sometimes, the contractor may choose to use this BRC, which come together in one piece of meshing at certain intended spacing and the size. There will be reinforcement bar in two directions, and those steel bars are typically welded together to form the square or rectangular grid fabric. The typical size it will be from 4 mm to 13 mm, which in this case, the whole piece of the BRC can be simply laid onto the slabs without requiring you to do the lining up and also tying together, as they come in the grip itself. There are basically three main types of the BRC that you can have in the industry: mesh A type, mesh B type, and mesh DA type. A type will have the spacing of 200 mm between the main bar and the secondary bar. As for the B type, the spacing is smaller for the main bar, which is 100 mm. As for the secondary bar, the spacing it will be 200 mm. That means type B is more heavily reinforced in terms of the main bar. The secondary bar it will be more or less identical. And the third one it will be more heavily reinforced. Both the main and the secondary bar will have 100 mm spacing. There are a series of the size, and there are standard names for those BRC. You may refer to the catalog from the local manufacturer for the adequate size. Either one will do. You can arrange the reinforcement bar as per what you intend it to be, or you can put good use of this BRC. It is only that this BRC is more rigid in terms of the spacing of the reinforcement bar, which is either 200 or 100. But if you choose the reinforcement bar is being laid and being tied together in the mesh for the slab, then you can have all sorts of spacing, something like 225, 250, 275, 350, even 400. Based on the design in the Eurocode, the spacing of the reinforcement bar can even reach to 450, depending on the conditions. However, normally the local practice would like to go for a bit more conservative in terms of the design. Some inherited the understanding from the BS at 110. Normally, the local industry will put the maximum spacing of the reinforcement bar to be 300. Whichever calculations that bring to you a conclusion the spacing can be more than 300, they will simply adopt 300s. That is not right or wrong on these issues, just that the designer choose to go for a more conservative design. And when you talk about the lapping, you are talking about the lapping of the BRC. There are two types of lapping. The first one, it will be full yield strength lapping. Another one, it will be half yield strength lapping. The full yield strength lapping means that the lapping length is sufficient for the stress to fully transfer from a BRC to another BRC. As for the half yield strength lapping, That means the lapping length is just enough for the partial distributions of the stress from a BRC to another BRC. The main difference in terms of the lapping are as indicated in the diagram here. They seems to be similar. The biggest difference it will be the reference points of that more than 25 mm. Let us cater for the half yield strength lapping. You are referring to the first crossing reinforcement, and there should be a minimum distance of more than 25 mm between the two crossing reinforcements. This 25 mm you will need to check carefully from the catalog given by the manufacturer. Some manufacturer may require it to be minimum 30 mm. For your informations, typically there will be a minimum of 25 mm as compared in the distance of the first crossing reinforcement. And this half yield strength normally happens when you want to lap the BRC across the beam, where you have two adjacent slabs beside the beams. You know that BRC for the slab are normally placed at the bottom of the slab, which is mainly meant to resist the tension stress generated near to the soffit of the slab. But when it reaches near to the support, the continuous slab will need to be reinforced at the top of the slab. As for the bottom BRC, you may use this half yield strength lapping to ensure the continuity of the slab crossing the beam. Next, we look at the full yield strength lapping. Again, we are measuring the distance between two crossing reinforcements. Just that the crossing reinforcement, one of the BRC it will be for the first crossing reinforcement, while another BRC we are talking about the second cross reinforcement. We are determining the distance here to be at least 25 mm. And this one, you will need to refer to the catalog given by the manufacturer. Some may require it to be more than 30 mm. If you still cannot observe the difference between these two, you can imagine like this. If you do not have the section here for the bottom BRC, that means this crossing reinforcement it will be the first reinforcement, and this will bring you to the half yield strength. The reason that it is full yield strength lapping is that you have additional section here that will give you a slightly longer overlap length, and this normally happens when you need to lap the BRC where the reinforcement bar is subjected to tensile stress. You want the stress to be effectively transferred from one BRC to another. This normally happens when your slab is relatively big, which is exceeding the maximum length of the BRC of 12 meters, that you require an additional BRC to extend the length, which in this case you need to ensure the stress is effectively transferred from a BRC to another. In this case, we will use the full yield strength lapping. And when you deal with the lapping, both under the conditions of the slab and also the beam, normally we'll prefer not to have the lapping at the midspan of the member, where the moment is at the maximum, because you also worry about the quality of the workmanship on site. Do they really accurately abide to the intended lapping length? So when you want to propose the lapping of the reinforcements, both in the beams or in the slab, try to avoid the high moment region. It is okay to have lapping just beside the support, where there is a high shear load, which in fact your lapping is beneficial. You have double layer of reinforcement bar, add up the shear resistance to the member. With that said, when you do the lapping, avoid the high moment region, and maybe you should go for the high shear region. And you need to consider for the congestions of the reinforcement bar, especially when you deal with the beam. Try to avoid all the reinforcement bar being lapped at the same place. This will significantly increase the amount of reinforcement bar over the cross sections, which can affect the performance of the member.